Hi, I'm Mark Barsamian. In this video, I'll be discussing limits of difference quotients. A key concept in this video is the important concept that I've mentioned in the last couple of videos, which I would say is the most important concept of the first month of calculus, and that is this. The important tools that we'll use are some of the same important tools that we've been using for the last couple of videos. These properties of limits in Theorem 2, remember that there are 8 of them. Theorem 3 about particular kinds of limits for rational functions and polynomials. Theorem 4 about a case where a limit does not exist. Notice that theorems 2 and 3 are about cases where the limits do exist. Theorem 4 is our only theorem about being able to say that a limit does not exist. And then the definition of so-called indeterminate form. All right, our first example is the following. Given this function, f of x, find this limit of this strange expression. Now, this expression is an extremely important kind of limit. It's called a difference quotient. The expression inside the limit is called a difference quotient. I'll talk about why that's called that name later. For now, we're just going to focus on finding the limit. Now, first note that we're being asked to find the limit of a quotient. So a natural question to ask is, what happens if we just try substituting in the value h equals 0? What happens if we do that? Well, let's try it. So you can see that we get 0 over 0. So that tells us that the limit is what's called an indeterminate form. Now remember that you can't find the limit of an indeterminate form by just substituting in a number. In general, if you are finding a limit and substituting a number into the limit causes the denominator to be 0, then you're not allowed to do that substitution. You have to find another way. So what do we do? Well, we're going to follow this strategy to find the limit. We're going to first get the parts needed for the expression. And then we're going to use the parts to build the expression and find the limit. So let's get the parts. We're going to need two things in order to build this. We're going to need f of 4, and we're going to need f of 4 plus h. For both of those things, it's going to be useful to have what I call the empty version of the function f. So remember that the function f with a variable inside is the following. And what I call the empty version is the same expression but with every x replaced by just an empty pair of parentheses. Now, to find f of 4, we just put 4 in the parentheses and simplify. F of 4 equals -3. To find f of 4 plus h, we put 4 plus h in parentheses and simplify. Now we're going to use the parts to build the expression for the limit and then find the limit. So remember that we start by writing the limit that we are being assigned to find on the left side. And then we copy down the limit symbol and replace the expression inside the limit with a new expression using the terms that we just built. So we go up and get f of 4 plus h, replace it with this expression. Then we go up and get the expression for f of 4, and we're going to put it here. So f of 4 is this number, -3. Now notice that the original limit was, as I said, an indeterminate form. Indeterminate form because if we substitute in h equals 0, we would just get 0 over 0. Well, notice we've now replaced these expressions with the formulas that they represent. And the thing that we now have is still an indeterminate form. But what we're going to do is simplify this expression. Notice that the minus 3 cancels the minus 3. So we rewrite the expression with that simplification done. Now, notice that this expression is still indeterminate because if we substitute in h equals 0 at this point, we get 0 over 0. So it's useful to rewrite this in a way that makes it clearer what is causing this expression to be indeterminate. So I'm going to factor out an h in the numerator. Now at this point we can see that the expression is still indeterminate because if we substitute in h equals 0, we get 0 over 0. But in this form we can see very clearly why it's indeterminate. What's causing it? What's causing the expression to be indeterminate is now this h over h. Well, wait a minute. We have information about h. We know that we're taking the limit as h approaches 0, and that tells us something. Since we're taking the limit as h approaches 0, we know that h is not 0, so we can cancel the h over h. Remember that that is the most important step of the first month of the course, knowing that you can do this cancellation. And the reason that we can do the cancellation, we had to say very clearly, it's because we know that we're taking the limit. All right, well now look, we've got a limit of a polynomial function, so we can use theorem 3. Remember what theorem 3 says. Theorem 3 says that if you're taking a polynomial function, the expression for the limit of the function is the same as the expression for, or the value of the limit of the function is the same as the value that you get if you just substitute in the x value. So that's what we're going to do here. We're going to use theorem 3. And that's our limit. Our limit is the number 5. Now let's make a couple of observations here. Sorry, let me go back up to this. Well, our first observation is that we started with an indeterminate form, and we simplified the expression, rewrote it until we got a form where we could see very clearly what was causing the limit to be an indeterminate form. What was causing it was the h over h. All right, well, then we cancel the h over h using the fact that we knew that h is not 0, so we could cancel it. Now, after we cancel it, I didn't write this at the time, but notice after we cancel the h over h, the form is no longer indeterminate. And so that's why we were able to use theorem 3. All right, let's do another example. In this example, the function f of x is 7x minus 5, and we're being asked to find this limit, which again is a difference quotient. All right, well, again, the natural question is, what happens if we just substitute in h equals 0? Well, if we do that, we're going to do the exact same calculation that we did in example 1, where we found that if we substitute in h equals 0, we end up with 0 over 0. And so this form is indeterminate. It's the exact same form that we had in the previous example. In other words, so limits of difference quotients are always indeterminate forms. Okay, so remember that you cannot find the limit of an indeterminate form by just substituting in a number. You just would get 0 over 0. So remember what we did in the previous example. We're going to do that in this example as well. We're going to get the parts needed to build this expression, and then we're going to build that expression and find the limit. So let's do that. First of all, we identify our function. It's f of x equals 7x minus 5. We identify the empty version. Then we find f of 4. And then we find f of 4 plus h. Now we use the parts that we just obtained to build the limit expression and find the limit. So remember that I start by writing down the limit that we're being assigned to find. And then I write down the limit symbol again, and I replace the terms in the expression with the expressions that we just found for those. All right, so let's make a note that we started with an indeterminate form, and replacing those symbols inside the limit with their equivalent formula expressions hasn't changed anything. We still have an indeterminate form. Well, we do what we did in the previous example. We simplify. The first simplification that we can do is cancel the 23s. Notice again, this is still indeterminate, but now it's very obvious why it's indeterminate. It's indeterminate because of that h over h. And we arrive at the most important step in the first month of the course. We realize that we can cancel h over h because we know that h is not 0. So we explain that clearly. So we arrive at this limit, the limit of 7. Notice that this is no longer an indeterminate form. So all of that simplifying that we did, okay, there wasn't much of it, but what simplifying we did do was in order to get it to this state where it was clear why the limit was indeterminate, and then be able to simplify to get a limit that was no longer indeterminate. All right, well, remember how to find the limit of a constant. We have a theorem, theorem 2.1, that says the limit of a constant is just the constant. So I can come down to our limit, and I can replace this whole limit expression with just the number 7. All right, let's make observations about what we did in this calculation. We started with an indeterminate form. We had some simplifying, and we arrived at a form that was still indeterminate, but it was clear why it was indeterminate. That was this form. Then we made an argument about why we could cancel. We could cancel h over h because we knew that h was not 0. We arrived at a new limit form that was no longer indeterminate, and so we were able to use a limit theorem to find that limit. Now, earlier in the video, I said that I will be telling you later what a difference quotient is, or why it's called a difference quotient. So let's do that now. Why is this expression called a difference quotient? Well, remember what the symbol f parentheses 4 denotes. And remember what the symbol f parentheses 4 plus h denotes. So in other words, these two expressions, 4 comma f of 4 and 4 plus h comma f of 4 plus h, they're the xy coordinates of 2 points on the graph of f. So the expression f of 4 plus h minus f of 4, that represents a change in y. That is, I could write that this way. And the change in x would be this. 4 plus h minus 4. But that's just the number h. So the expression f of 4 plus h minus f of 4 divided by h is just the change in y divided by the change in x. Now, instead of saying the change in y divided by the change in x, we could say the difference in y divided by the difference in x. In other words, a quotient of differences, hence the name difference quotient. That's the end of this video. Thank you.